Okay, when we're using these methods, disc, washer, cylindrical shells, we don't always rotate around one of our axes. That's why I want you to understand the process and draw out the pictures and draw your representative disc or washer or shell. And that will make this a lot easier if you actually understand the calculus. Don't just memorize formulas. Okay, so got a couple of examples here. And I think in all of these, oh, yeah, all of these examples, I'm just going to be going through some work that's already done. So I'm not going to be doing any of the work by hand here. I know as a student, I prefer to watch the math appear in front of me. I hate it when somebody kind of reads through math that's already on the screen. But I'm really in this video talking about the method and not focusing so much on, well, how do we do this definite integral? We'll do some, you'll watch me write up some examples in the next video. Okay, I hope that makes sense. So read this, pause and read, make sure you understand what's being asked. Okay, so we've got this line, y equals 4 minus x, bounded by the x and y axes here. We're going to take that region and rotate it around, not the x-axis, but the line y equals -2. And we're going to find this volume. Notice here that the inside is empty. So it's kind of hard to see in this picture here, but everything inside here is empty. So this is like a cone with the top cut off, and then a cylinder is cut out of it. That's what's going on here in the picture. Okay, so we can't just use some formula. We have to understand the process. So we're going to use the Walsher method to do this because we have a cavity in the center. Anytime you've got a cavity in the center, you can't just use discs. Okay, so like for clarity, I want to make sure you understand what I'm talking about. This stuff here doesn't exist inside there. Now, the blue is wrapped around there. I'm saying there's like a soup can missing from this cone. Okay, so we're going to be stacking up washers along the x-axis. So we pick some random x value and we draw in a little rectangle. If you draw in your rectangle, you're going to get these right. If you don't, you're not. So imagine that rectangle rotated around. So this stuff in the middle is going to be left out. We're going to have some washer that kind of goes like this. And it has some thickness. I cannot draw these with thickness. It has some thickness delta x. Soon as I write delta x, I know I'm integrating with respect to x. I know everything I write needs to be x's. I need my limits to be x values. I need my functions to all be functions of x. Okay, what's my outer and inner radius going to be? So here's what we've been calling R2, the outer radius, and here's the inner radius. It's not just the function, because here's my axis of rotation right here down at -2. So what's this distance all the way up to the top? So maybe I'll draw it here. Here is what I mean by R2. That total distance. It's not just 4 minus x. That's this. This distance is 4 minus x. I've got two more on top of that. So that distance is 4 minus x plus 2. What about my inner radius? That's just here. That's this distance here, what we've been calling R1. Right there, that distance, the distance for the cavity. That's 2. So like in the formula, it's, pi f squared minus g squared dx. F here is not the top. It's not the outer radius. The outer radius is f plus 2, and the inner is 2. So again, I'm not going to go through all the little steps in the integral. I'm trying to get you used to setting these up. We'll do some full examples where I write everything down in the next video. Okay, so just cleaning up here, that outer radius, 4 minus x plus 2, that's just 6 minus x. The inner was 2. So we get the integral. We got to find our limits. What x values is this true for? Is this guy always, is what I wrote here always the outer radius the entire time? Yes, for any x value you can think of, this distance from center to top is always 4 minus x plus 2. And for any x value you can think of, the inner radius is always 2. That's important, that outer and inner, these formulas we wrote are correct the whole time. For which x values? From here, x equals 0 up to x equals 4. So there are my limits. And then like you can check the details there. Okay, let's do another example. Now we're rotating around the y-axis, or not even the y-axis, something parallel to the y-axis, the line x equals 1. So we're rotating around this way. Like, just think about this. If I'm rotating around like this, I need my washers to look like this. I need a bunch of washers stacked on top of each other that have that same rotational symmetry. That tells you right there that your delta, which is the thickness of these washers, is going to be a y. Everybody needs to be in terms of y. Your limits, your functions, your differential, you need a dy. That's the first thing you got to think about. Am I going to have dx or dy? Secondly, let's draw in what our region's going to look like. Oh, nope, that's not it. We're not rotating around there. We're rotating around here. So this needs to be right in the center. So instead of being 1 unit here, I need to go 1 unit here. So this is what the other side will look like. And then we're building some kind of volume that looks like this. Draw in one of your washers. They did a much better job than I could. Always draw in one of your washers and draw in this representative rectangle here that is getting rotated around to build that washer. Listen to my words. I know you've heard me say this like 30 times now. If you draw the little rectangle, you'll get these right. If you don't, I guarantee you you're going to get these wrong. That's my little delta y there. That's that thickness. My outer radius from the line of rotation, which is not what I drew, from the line of rotation to the outside of that particular washer there is this distance here. I need these to be in terms of y, not x. So this red line here, I need to think of that not y equals x over 3. No, I need x equals 3y. That's the outer distance. So let's call that R2. And then the inner distance. Oh, and I lied. That's not true. That would just be this guy. From here to here would be 3y. I've got an extra 1 there. That entire distance from the midline to the biggest radius. Don't think up and down. When you're going around the y-axis, you got to think left and right. That radius, the outer radius, is 3y plus 1. So R2 is 3y plus 1. Okay, what about the inner radius? Again, I need everybody in terms of y. I need x in terms of y. So that guy there, no, I want x equals y squared. Then this inner radius here, there, which we would call R1, this was R2. That distance is y squared, that's right there, plus 1. And of course, they wrote it in the other order for this particular example. So I don't want to confuse you with that. I want to pause and rewrite this a little bit. Okay, I don't want you getting caught up on who we call 2 and who we call 1, because we're going to look at examples later where they do it the other way. So think outer and inner. So I'm going to call this here R out, or R big maybe. And this will be R small. To the bigger and the smaller. Excuse me. That's what matters. It's bigger minus smaller. Bigger minus smaller. Okay, so there's the bigger one. There's the smaller one. And you can look through all these details. The main key here is setting this up. So bigger minus smaller. They went ahead, they cleaned that up before throwing it into the integral. You can go through all the steps and do this integral on your own. You probably should. I'm just trying to get these set up. Okay, let's look at this guy. So we're rotating a lot around the line y equals 4. So think about if we're rotating around like this, like coming out at your eyeballs, ooh, rotating around like this, all of our washers are going to be stacked up. We're going to have a bunch of washers. Maybe they're getting bigger, maybe they're getting smaller, but they're all stacked up horizontally. So we're going to have delta x's. That's the first thing you think. I'm going to have delta x's. So then draw in one of those washers. Pick some random x value here and draw in this little rectangle, because that's what gets rotated around. So the top of that rectangle is going to be up here when it gets rotated. And then you can try to draw in, it's I would say mandatory to draw in the rectangle. You can try to draw in the washer, but if your drawing skills are as bad as mine, it might not look very good. Okay, so try to draw in a washer. And again, these lines right now, I'm coming out at your eyeballs. And now on the back end, I'm inside the page. I'm going behind the page, out towards your eyeballs, inside the page. Okay, so as soon as we see, oh, I've got some delta x there, I know everybody needs to be in terms of x. My outer radius. My outer radius is the distance from my rotation axis to this bottom curve here. And he's already y as a function of x. So that distance is, let's see, this whole thing, this is going to be tricky for a second here. This whole distance is 4. This distance right here is 1/3 x squared. So this distance is 4 minus 1/3 x squared. Think about this for a second. I want from here to here. That's what I'm trying to find at the moment. The whole thing from top to bottom, from the x-axis to there is 4. This distance is that y value, 1/3 x squared. So this distance from the midline to the outside of that washer is 4 minus 1/3 x squared. And then here, I'll use a different color. This distance here, the inside, so this one, let me go back to red. This is what I was calling R big, the outer one. And now green, same idea. This distance here is x. The whole thing was 4. So this green line here is 4 minus x. So R small is 4 minus x. Okay, what x values am I using? Let's check a few things. As I go through from start to finish, is the outer radius always going to be this? Do I ever change functions? No, I'm good. Sometimes you do. Sometimes in the middle, you've got a new function. Is the inner distance always going to be the green, 4 minus x? Yes, right here at x equals 0, the distance is 4. Up here at x equals 3, the distance is 1. 4 minus x, 4 minus 3. So yes, all along this region here, this is always the larger radius. That's always the smaller radius. Okay, for which x values is that true? From x equals 0 up to x equals 3. So you can read through all these details here. There's my outer. What I got these from Khan Academy, these ones we're looking at now. And they call the outer one R1 and the inner one R2. Who cares what you call them? Think outer and inner. And then they cleaned it up first before throwing it in the integral. And again, definitely you should go through and check all these details. Our main goal right now is setting these up. Okay, that's all I've got in this one. That's a good place to stop.